Okay. Well, hello guys again. Welcome to our Meeting of Waters. That's an initiative from the CEPAS, the Groundwater Research Center at the University of São Paulo. And this initiative is also supported by FAPESP and using two main projects. One is a SACRI project. That's one project that is coordinated by this institute, the Institute of Geosciences at the University of São Paulo, and also by a sprint, supported by the FAPESP. Okay, the idea basically for these meetings, or Encontro das Águas in Portuguese, and also Meeting of Waters, is to discuss water in different aspects. And today you have the pleasure to have two visitors from Japan that also participate in the project with us, with the group of SACRI, and they are visiting using the money from the University of Hiroshima that also support this project. And also after I'm introducing the Professor Onodera, full professor at the University of Hiroshima, and after his talk, Mitsuyo Saito is also speaking about hydrogeology in Japan. I think is interesting because normally from Brazilians, we don't know much about Japan, except for sushi and sashimi foods. That is pretty common in Brazil, mainly in São Paulo. That, of course, I love because of my family also. I'm descendant from Japan, Japanese, and but sushi, sashimi is pretty common. Sometimes not good sushi, sashimi as a Japanese standard, but also it's a very, very common food for us in São Paulo. But except for that, normally people don't know much about hydrogeology, and I think that's a good opportunity for two things. One, to know about the hydrogeology in Japan, problems of contamination, problems of interaction of big cities and the hydrogeological cycle. That's Mitsuyo presentation. She's speaking about this impacting in a big city, a metropolitan big city in Japan. But also note this, but for us at the project, at the SACRI project, that is an ongoing project. Actually, we just started. We are in the first year of the project. The idea for us is to know, based on the Japanese experience, and try to apply some of these technologies, apply some methodologies or ideas here, and vice versa. Actually, because in Japan, they have projects, and that our group in Brazil is involving more and more deeply. I think that's a very interesting moment to have this type of connection, link, and cooperation. Because of this, I think that Encontro das Águas, this meeting, or Meeting of Waters, is an excellent opportunity for this type of interaction. I just want to mention that this is hybrid event. It's very common now because of the pandemics, and you have a better audience that is receiving our sign and in YouTube, okay? And also you are recording this presentation for YouTube, and after the recording, you get access for everybody. It means that is interesting because you can have this presentation personally here for you guys, and also you can access again if you want something. And of course, we are open a period for discussion, questions, and clarification necessary. But also, mainly for people from YouTube or for that can watch this presentation after, I think that it's possible to direct some questions or ideas directed to us at the SACRI Secretariat and you can put in contact with the Japanese researchers, or also with us, because we are pretty close to them. Okay, I think this is the short presentation, and I really want, it's a great pleasure for me to introduce Professor Shin-ichi Onodera. Shin-ichi visited us many times and worked in some projects here in Brazil. He's a professor, a full professor at the University of Hiroshima University in Japan. It's a very nice university and very well known in its area of hydrology, hydrogeology. And Professor Onodera Sensei, is received his PhD in Chiba University in sciences. That's normally is interesting. This system in Japan, that is the guy has a more broad training for sciences. But I give you the space, the audience, to Professor Shin-ichi Onodera, that he's speaking about nutrient cycle in Japanese urban and rural catchment for a recycle system. Okay, thank you for accepting this invitation, and thank you for visiting us for this short but very productive period. Okay, thank you.
Okay, thank you for the introducing, Ricardo. Okay, today I talk about the nutrient cycle, because now nutrient is sometimes a big issue in the world. So, for example, the nitrate pollution is a big issue, and including the phosphorus, that we have some big issue with eutrophication in the coastal zone and lake. So then we talk about the nutrient cycle in Japan. But Japan is the different way from the Brazil. So then, for example, the depopulation, some rural areas. So that one is a big issue. That is the village close and people know, and also the aging is a big issue, also social. So then we will consider that social issue and also the pollution issues, that connection. So then we talk. And finally, our goal is a recycling system to application to the catchment, and especially agricultural land. So that one is also sometimes so useful and available. Okay, I start. So my ongoing project is number 1 and 3, 4. So then my trip to Brazil is covered by the Hiroshima University, the promising research initiative of the title is Healthy Cycle in Asian Catchment, including Japan, different social issues. Okay. Then, basically, I want to talk about the global scale nitrogen and phosphorus cycles. So this figure shows the atmosphere and the land and the ocean, that connecting the cycling of the nitrogen. So this is Ruben Galloway's the top figures. So then this blue arrow showed natural process, and the orange one showed the artificial, the anthropogenic one. So as you know, that the large thickness, that arrow, meaning the fertilizer application. Fertilizer mainly come from the produced by the atmosphere's nitrogen, and that's after the application to the agricultural land. That one, that cycle, then also the coming to the ecosystems. Then this, that cycle, that nitrogen cycle in ecosystem is so huge, rather than the application of the anthropogenic. But also that the nitrogen deposition from the atmosphere. That one is also big, and totally the industrial country and the developed country is a big issue. But now China and India is a big issue in the atmospheric depositions. The balls, so input to the land. After that, the cycle. Then, so that in some case we can face in the nitrate pollution, and also there's some case in the eutrophication, and also that some nitrogen decomposed by microbiologists and the denitrifications. There's some nitrate made produced to the nitrous oxide. That one is also the big issue to the global warming. So greenhouse gas. Also, that I want to show that the trend of the fertilizer application from 1960 to the 2000. This figure comes from the Tillman's, also the Nature papers. So the blue one is nitrogen, and the green one shows phosphorus. So both is a so important material to the fertilizers. So then the last 50 or 60 years, so that fertilizer application increased. The nitrogen case is 10 times, and the phosphorus case is 3 times increased. Also, the irrigation water also increased. So on the other hand, that the bottom figure shows that efficiency of the nitrogen fertilizers to the crop. So if 100%, meaning that the total application fertilizer is absorbed by the crop, but that that value is less than 100. That meaning that some value of the fertilizer lost to the environment. So then 1960 value is 80%, but recently that value is totally less than 30%. So that meaning that 70% of the application of the fertilizer was lost to the environment. That meaning that sometimes pollution, sometimes eutrophication occurs. And the next, I want to show that global scale phosphorus cycles. So this green color shows the natural environment, and the white color shows that anthropogenic systems. So mainly that phosphorus cycle starts from the rock, phosphate rock. So then this rock sometimes produced to the phosphorus fertilizers. So then apply to the soil in agricultural land also. So that, and the half of the fertilizer pass to the crop, and also go to the human. So this also showed this part, the fertilizer and application and the agricultural land cycle. That one is mainly rural. And the human area, meaning the urban. So that phosphorus cycle, the rural to the urban, the connecting. So that firstly, my title is including urban and rural, meaning that the phosphorus cycle is so important, also the nitrogen cycle. From starting point is rural, then after that urban. So then part of the fertilizers, the loss to the environment. This one is totally process is erosion, soil erosion. Okay, the agriculture and the versus and the environment, that already I showed the Tillman's papers. They indicated that fertilizer has been applied with high increasing ratios. And also that, however, the fertilizer efficiency cereal production has decreased up to 30%. This means fertilizer loss in agricultural land was one of the big issues for the environment. Okay. So the nitrogen case, the totally leaching. On the other hand, phosphorus case, the soil erosion. That's meaning the flow path is quite different. Nitrogen normally pass to the groundwaters, and the phosphorus come to the river and the surface. So that one is a different way. But totally, we have to discuss in the catchment scales. So because of that meaning that not only surface water but also groundwater, we have to consider that also that sometimes interaction so important. So next I want to give you the information of the fertilizer consumption from 1960 to the present. Then there are some countries based data. So this blue color meaning China. Now the China is a huge using application countries, but also the orange one, they're also increasing so serious. That one is India, second country of using the application, and the gray one is a stable trend now. That one is the US, and this yellow meaning Brazil. So the Brazil is also the nitrogen fertilizer application, the fourth number countries. On the other hand, Japan, this red one, the decreasing trend now. So then the number is just 28. So that's Japan is a so small country, but also as you know that I will show that later that the Japanese agriculture system is quite weak. So, but the next indicator is a different way. So that indicator is just fertilizer consumption per unit area. That meaning that just similar to the concentration of the fertilizer. So that value is that Japan is the second country. So this meaning that Japanese agriculture that have some image to the good quality of the crop. That this value is larger than China. Also Brazil. Brazil is lower now. Okay. So also that some social issue I will give you in Japanese case. So this paper that published by the Hayashi, this is also Japanese researcher. So that the recent papers in the environmental pollution. So then they mentioned about the nitrogen budget in the Japan system, and also that they mentioned about the decreasing trend of nitrogen. So because the one reason is that food, the self-sufficiency ratio decrease quite big values, and also the aging. Now Japanese population qualities that change. So aging is a so serious way, and the population value is stable. Some recently that decreasing. So that's meaning that activity, especially agriculture, that one is a little bit decreasing. So that social trend, meaning affect to the also nitrogen loss and nitrogen fertilizer using also. So that's meaning that also nitrate pollution recover in the future. So then also key they show that the reactive nitrogen loss in Japan from 2000 to 2015. So total value decrease with the main part is cropland application is a little bit decreasing. And also the wastewater, also the little bit decreasing. Then totally decreasing values. So the total Japan, all Japan area, so nitrates pollution that not serious today. But we have to take care so that after our topics. So then today I want to talk about my presentation goal to understand that to understand the nutrient cycle in the rural, also urban catchment, especially Japan. And also the second one, confirm the availability of the mitigation process such as the recycling system. But today is the first one is the most important talk. Okay, next I want to talk about the urban system nitrate pollution and nutrient cycles. So mainly our project two we have. So that third one is Asian countries, including Japan, China, and Indonesia. So China is totally the developing and two developed countries now. So that one is similar to Brazil, but so serious environmental issues here, there. And Jakarta is now developing countries. Then also the population still increasing. Also that agriculture activity is so huge, similar to China. Okay, so I will show the Japanese case. So this figure, the general information that's above one, that's population change and the industrial production index change from 1940 to 2000. And the bottom one shows that the water quality in surface water. This orange one is a river, and blue one is coastal water. Totally, you can see that from 1950 to 1970, so river water quality. So that value is COD is so seriously increasing, rapidly increasing with population increase. So we say that classify that's the urban development. So developing stage, I just defined. First developing stage, and the second developing stage, third developing stage. First developing stage meaning population rapidly increasing and surface water pollution seriously. And the second stage, as you can see, that population stable, but still industrial production increase. And the water quality, that little bit recovery, the surface water quality, little bit recovers. Because of this period, totally the construction of the infrastructure start. Construction meaning the infrastructure meaning the sewage system and other treatment systems. So then surface water quality increase. Then third stage meaning that totally economic the activity decrease. So then surface water quality also rapidly decrease. But as you can see that seawater, coastal seawater quality not so recovers. So that meaning that similar to groundwater. So we can find the confirmed already. We could confirm already. The second stage we can see the subsurface pollution accumulation started. So that pollution stage, the change from first stage to second stage, from surface pollution to the subsurface pollution. So that one is an interesting point. So then that process is the general information, but we can apply to that definition to other Asian countries also. So then I want to talk about the Osaka Bay catchment. Part of the Osaka Bay catchment, we say the Yamato River catchment. So that river is the most serious quality rivers in Japan. But now that totally recoveries, but the former period, for example, around 1970 is so polluted. So then also the Osaka Bay, also the so polluted and eutrophication issue is so big. Okay. So that land use change also we can see. The pink color shows the residential and urban areas. The yellow color shows that the agricultural areas. Mainly this catchment covered by the paddy. Paddy is a rice field. And the green color shows that the forest. So this forest covered only the mountainous areas. So then the flat topography totally used by agriculture and residentials. From 1970 to 2000, so that we can see that pink color increasing, residential, urban increasing, and yellow color decreasing. And some green color also decreasing. So based on that land use change, so also the effect to the nutrient cycle in the catchment scales. Okay, then we apply the catchment scale hydrological nutrient cycle model, SWOT. SWOT model is developed by the US the agriculture something. So that this model is more suitable for the agricultural land. But we apply also including the urban areas. So that we need to consider that the sewage system and also some application, the social issues also. So then we collect the topography, land use map, and soil map. Then we make the using a GIS. Then the hydrological response unit in catchment, that totally more than 3,000. So that means that just each scale, each HRE hydrological response unit scale is totally 500 meter grid. So then we can consider the spatial distribution of the water cycle and nutrient cycles in each HRU. So then we collect weather data, runoff data, nutrient data. So then we can calibrate. If we calibrate and validate good, so that case we can after the optimization, so that we can use that models to some scenario analysis and forecasting. So then, firstly, I want to talk about urban zones, especially the paved effect. So then we just defined imperviousness ratio. That meaning that impervious area divided by total area. So then we talk that the percentage of the imperviousness of the urban regions. So this is a former period, and this period is the present period. So the totally imperviousness value increasing to the recently. So that each process change also with imperviousness of the urban regions. So for example, the groundwater recharge ratio quite decreased. So that if 50% of the imperviousness, that means that totally less than 10% of the water balance. And also surface runoff also quite increasing. So then also evapotranspiration ratio also decrease up to 50%, the same value, but after increasing of the 50%, in that case, they will decrease. So we can define the water budgets using is considering the imperviousness in the urban zone. Also, we focus about the forest part. So then we compare the SWOT model output and modest meaning the satellite data. So that both the evapotranspiration values, the comparing, that good the correlation values. So then we can define that SWOT model output of the evapotranspiration is so good. So then we apply to the different age, so 10 years before and 20 years. So then we discuss the evapotranspiration change from 1980 to 2010. So also that we can estimate the each part of the evapotranspiration. This is a direct soil evaporation, and this part is just transpiration, and this part is just the canopy storage, after canopy storage, that evaporation. So that three parts we can separate, estimate. So then, also, as you can see that from 1980 to, for example, that four name is different mountains. So meaning that different coverage of the forest species. So for example, Ikoma area, you can see that evapotranspiration totally increased. The total value is increasing value is 200 millimeters. So this region, the total precipitation around 1,200 and 300. So that 200 meaning more than 20%, nearly 20%. That water loss is sometimes big issues. So why? So this increasing occurs. So first one is growing of the forest. So the forest growing meaning the canopy trap also the big. Also the growing speed increase meaning also transpiration increase. Okay, so then we can discuss about also another meaning, carbon dioxide also increasing last 30 years. So that effect also the growing speed also increase. So then evapotranspiration increase. So we can detect it. Also this meaning is another meaning. So that forest growing is also in terms of the nutrient captures. So that if in case of in terms of the nutrient trap of the polluted waters, so in that case, so suitable in that case. Also next I want to show the nitrogen budget in Yamato River catchment. So then including population and sewage and the human waste and also fertilizer in agricultural land. So then, as you can see, that the SWOT model analysis show that the nitrogen discharge peak is around 1980s. So before 1980s, we don't have enough data of the monitoring data, but using that SWOT, so we can reconstruct of that value, real values. So then we can reconstruct before 1970s. So then totally we estimate the nitrogen discharge the last 80 years, so using that models. So this case, we need to the good land use map but we have sometimes land use map in the around even 1940, before the Second World War. Okay, so also that using this data, so that we can discuss about, for example, the precipitation and non-point source nitrogen load. So that one is also the good correlation. So in that case, so we can also forecast in the future. So now climate change impact is so serious. So in the future also that we can use this correlation, so we can forecast how much nitrogen discharge in Osaka Bay. So now firstly I say that Osaka is quality is now is better than former, but sometimes climate change impact. So sometimes a big issue to nitrogen load to the Osaka Bay. So we need to discuss using this. So then also that we compare the other rivers in the world. So then based on this comparative study, so we can say that Yamato River Osaka case is a so serious peak nitrogen load. So that case is, that is just per hectare. So this value is the double of the U.S. river, the urban rivers. So in that case is so Asian characteristics. Sometimes the Asian country and China and India is a different way, but other China, Philippines, Indonesia is the small island. So in that case, it's similar serious situation. So we should share that information for manage of the nutrient discharge. Also, then phosphorus scale. Also, we can estimate the phosphorus discharge. Not only phosphorus discharge, but also the phosphorus cycles. Phosphorus cycle is a little bit complicated because sometimes the phosphate is absorbed by many soil, the clay and organic matters. So then that's meaning not soil. So then that trapped the surface soil. Then after that, that absorbed in the ecosystem, mainly the vegetation and the tree. So then after that, the ecosystem cycles. So that case is phosphorus naturally they're trapped in the ecosystems. But if we destroy also some disturb that ecosystem, in that case phosphorus release easily. So then we can discuss. So using the SWOT modeling that including forest site and agriculture land urban zone. So then we compare the other countries' result. So then this is the cycle that, for example, the fertilizer, phosphorus fertilizer application, the manual phosphorus application, and the crop phosphorus uptake. So that's value. Then we can estimate the remaining value. So that value, the potential of the release. So then that value is that value is the stock of the soil. So then totally that value is stock of that value is the release of the percentage. So then the release value is that other country totally 50%. But in Yamato River case is very low, totally 23 and 20, around 30%. So this value that's also the similar estimations. So because sorry, my animation is bad. Okay, then Japanese case is sometimes a different that special soil cover. So that volcanic soil that we say andsoil. So that soil is the most strong absorption capacity of phosphorus. So then that's the absorb capacity is so high in the catchment. So then finally we can make that the phosphorus stock in where is the big stock in phosphorus in the catchment scale. So using this one, so that for example that the living vegetation also the stock, and the soil stock is totally big in the catchment scales, and also that we should consider that the riparian stock. So that value is totally the 5% of the discharge, total discharge. So this one also that not so that small, negligible. So we need to consider. So the phosphorus cycle case also that we need to consider that each part is so important. So that meaning sometimes we should consider the riparian, the vegetation and riparian, the sediment is a good way of the stock. Then, but that value is case by case in climate and topography. So we need to collect more data and more other catchment. So also we need to compare comparative study in the futures. Okay, next I want to show that the rural areas contents. But this is last year because those IAH conference I already talked. So that's shortcut. So that small island, Ikuchi Island in Hiroshima prefectures. So this island I went to with Ricardo and Fernando also then. Then that citrus island. So that meaning that so high fertilizer application areas in Japan. So that totally annually 240 nitrogen application. So that one is a so huge values. So then and also the top of the mountain is around 500. So that's a small island. Then the distance of the top to the coastal zone is totally 2 kilometers. So then that slope is so steep. So then groundwater also the so quite high gradient flow. So then I didn't give the mention of the geologies. So maybe that granite island, this one. So then, and around 15 meters below, so we can see that the weather rock. So then that around up to the 30 meters that we can see sometimes bedrock of the fresh rock. And also the surface layer, the top 10 meters, that one is some deposit of the collapse, that landslide, that sediment. So then, so that totally water hydraulic conductivity is higher in the around 50 meters deep and also 30 meters deep. That zone is high also. Sorry. So then this another figure meaning nitrate and nitrogen concentration in that groundwaters. So as you can see, that value is 10. That's standard value of for the pollutions in WHOs. So the totally 70% areas that are polluted by the nitrate and nitrogens. But the coastal zone around the 300 meters, so that the concentration quite decrease quickly, drastically from A to B. So this meaning that just denitrification occurs. So we confirmed by the nitrogen isotopic property and other chemical approach. So sometimes we collect that nitrous oxide and nitrogen gas. So that totally that indicators show that denitrification occurs. So, but this polluted groundwater sometimes we can use to directly irrigation to also the agriculture without apply to the fertilizers. Okay, then another island I want to show that because this one on that we focus about the social issue impact on nitrate pollutions. So then two villages there in this island. So mainly this island, the geology is liolite. That's similar to the granite, the minerals, but the porosity is different. But the same meaning, also the topography is the same. So the groundwater flow that we expect the same, similar way. So, but the social status is a little bit different. So this could be meaning the central village, and the Ocho is the eastern part of the village. So then, as you know, Ocho is double of the population. So then, also the average age is 73, rather than younger, but totally similar. The Kubi's average is 76. So, but this one is high population, large population, and a little bit younger. And also, agricultural land is the 3 times. The Kubi is only 0.6, but the Ocho is 1.6. So that means that agricultural activity is higher in Ocho. So that's social and human activity, how affect to the pollution. So then we apply to the nitrate concentration detecting, and also the nitrogen isotopic value also detected each village. So that's color show that the concentration and the circle size, meaning the nitrogen 15 data values. So the small value is similar to the 0. That meaning that similar to the using the chemical fertilizers. But the big size of the circle, meaning the 10, more than higher than 10. That meaning that manure and the organic fertilizer using. So as you can see, this Ocho is a little bit higher circles. So that means manure, also the organic fertilizer used there. And the concentration color little bit light in Ocho. So that if we apply the fertilizer, organic fertilizer, that one is not serious leaching of the nitrate. So then pollution also the little bit the not so serious. So then based on this data, we can say that the social activity is sometimes affect to the pollution issues. So this is just quantifying the approach of the CF is a chemical fertilizer, and this one is the organic fertilizer, and this one is a sewage. So the Ocho and Kubi is a sewage contribution is not so high, and Ocho. Sorry. This OF is organic fertilizer, and CF middle is chemical fertilizer. So then Ocho is a little bit higher organic fertilizer using, and that could be using by the chemical fertilizers. So that one is that we just quantifies. So then the totally summarize that we can summarize that the social activity and the associated with the nitrate pollutions. So then finally we suggest and also that recommend that nitrogen water recycling systems. So similar to these schematic diagrams. So that the eutrophic polluted, nitrate polluted groundwater is to use to the agriculture crop. Even that orange citrus situations also. So then the eutrophic groundwater, if we use the irrigation, so that case the fertilizer application value also decrease 1/3 of the former situation. So we can cut of the fertilizer application and also using this system. So also that environment meaning the pollution issue also the recover using these systems. So then we will discuss. So finally, I want to conclude our topic, today's talk. So we are approaching to the complicated nutrient cycle in urban, rural areas in Japan, because Japan is a so small island and also the complicated topographies. So then also this the result also we can apply to the other Asian countries in the future. So then this totally we propose to the sustainable, suitable recycling system of the polluted waters using SWOT model and tracer approach. So today I mainly mentioned about the results of the nutrient cycle by the SWOT, the quick discharge in urbanized areas, and the high potential of the nutrient stock with forest growing, and also the riparian sedimental vegetation, also high nutrient discharge during the rain, and also the uncertainty of climate change impact. Also then by using the tracer, we confirm high impact of the aging and depopulation on nutrient cycles in the small island. So finally I want to recommend the recycling system of the water and nutrient into the agriculture land, and also in the future forest land. Okay, thank you for your attention.
Thank you, Shin-ichi. Nice presentation. That's really interesting. And during your presentation, I thinking about our unknown about the nutrients in agriculture area in terms of groundwater. I know that the people from agronomy is much more developing this area, but when we speak about the deep infiltration, that's much more complicated for us because we don't have extensive and a good monitoring system that can catch this. Mainly in your case, calculate the amount of nutrients that can get the aquifer. I opened some questions, short questions for the audience, and after that, invite Mitsuyo Saito for the next presentation, and of course you have time for discuss the two presentations together. But I think that if someone wants to ask or some clarification about the presentation, please suggest you. Okay.
Yes, it was a very interesting presentation to me. I mean, I'm from chemical engineering. some of your slides suggest to me, particularly when you have this large change in crop productivity with an increase of nitrogen input as fertilizer, do you have microbial adaptation phenomena happening? So you start off with low nitrogen use or low nitrogen soil. You start applying fertilizer. Initially, the crop responds well. You have a strong increase in production. Response starts dropping. You put more fertilizer in, and then as a consequence, you increase the amount of competing bacteria and compete for nitrogen source. Is this an effect that's happening there? And the connecting question is whether it would also be interesting to look at ways of changing the way that nitrogen is supplied to plants in agriculture. Looking at other ways to better targeting the nitrogen to the plant needs.
So you mean that's this slide or that?
Yeah, it was the first time, but here as well. Yes.
Yeah. So that this area is I informed that the topography is steep,
Yes.
so the groundwater speed is also high. Then the totally citrus coverage is 30% in the catchment. So without except of the mountainous slope, so that around 100 meter altitude to the beach, so we can find the coverage of the citrus. So that meaning that totally everywhere the fertilizer applied. So then the fertilizer reaching everywhere occur. But I want to show that the downstream zone is only redox situation. Then that case is we cannot use that to the irrigations. But our idea is, for example, the highest point the pumping well to the using to irrigation. So then, for example, the 100-meter height areas, so we supply to pumping. So then using a solar system, so then continuously the irrigation. But also irrigation system, we use that drop irrigation, that's so small irrigated amount. So that case is that water use also not so much. So then we can cover the totally wide areas. But the big issue is just the cost of the pipeline and something. So then we don't the coverage, the big coverage, only the less than the 10%. So lens also that.
You would have to intercept the diagram, and you would have to have a barrier to catch all this contaminated nitrogen, contaminated groundwater before looking up to the surface.
Yes, so that around more than 20 milligram per liter, so we can use it.
Any other question for the moment? Or can save the question for the end of the two presentations? Okay, thank you, Professor. And okay, the next talk is about a little bit different, but I think in a complementary way. Professor Mitsuyo Saito from University of Hiroshima now speaking about big cities and impact of groundwater and sewage system in the coastal Osaka megacity. It's a different approach and a different. She's putting a little bit more complication in this study in the coastal area because her PhD also was that at the Hiroshima University was related to this discharge in coastal area, groundwater discharging aquifers of below the sea, and then that the sewage and the nutrients, that's the same of Onodera Sensei. Well, Mitsuyo Saito now is an associate professor at the University of Hiroshima University, but previously she was a professor at the Okayama University. And that when she visited first our country, that she helped us a lot in some studies that the CEPAS developed here in São Paulo, and try to help us to understand the balance of nutrients, or mainly nitrogen, in some agricultural areas in the interior of São Paulo. And also she's still going this. And for our project, in the SACRI project, the thematic project, there's a specific areas that we are studying the impact of agricultural activity. Actually, both Japanese researchers help us to understand this, because I don't know for the audience is really one. We have a very big question mark about the impact that we expect from the agricultural activity in our aquifer in São Paulo, in the state of São Paulo. You have to consider that. I think in terms of development and we know. I think it's pretty in a good level impacts in urban areas, but when you go to the rural areas, that I can say that we don't know much. And please, Mitsuyo Saito, your presentation. Thank you.
Thank you, Dr. Sensei, for your introduction. So thank you for joining today's seminar for everybody. So can you hear me, my voice? Okay. So yeah, so I'm Mitsuyo Saito from Hiroshima University, Western Japan. So today I want to more focus on the urban area. And but I did mistake, so I forgot to include the funding information. But so this work and my visit is supported by a project of the Shin-ichi, the Asian Pacific Network project, and the JSPS project, by my own project. So today, the sample part was already explained by Shin-ichi. So I also want to give a talk about the groundwater situation in Osaka, megacity. And so more focus on the groundwater overpumping impact and the sewage network system impact on groundwater environment Osaka. Okay, so this is just a brief introduction. So yeah, as you know, there are so many big cities in the coastal area in the worldwide. So this figure shows firstly the LEC red. This is a low elevation coastal zone, which altitude is less than 10 meters. So you can see this color legend. So the warmer color shows more population lives in the low elevation coastal area. So that means the clear region is Asia. For example, in China, it's more than 200 million people live in the coastal region. Yes, and another information in this circle shows the allocation of the megacities, in which the population is more than 8 million. So this darker blue shows the megacity in 2010, and the light blue circle shows in 2025. So you can see that Rio de Janeiro is already megacity in 2010. And also you can see the much more megacity located in the coastal area of Asia. Yes. So there should be the huge, significant impact on the human activity on coastal region. And now, today I'm talking about Osaka in Western Japan. This is of course, one of the megacity in Asia. So this is a schematic diagram of a coastal groundwater squeeze by human activities. Of course, there are several the impact of human activity in coastal area and coastal groundwater. So they mention about mainly 9 the significant impact and human activities on coastal environment. And I think today I want to talk about the focus on the number 1. This is a seawater intrusion to coastal aquifer by overpumping of groundwater. And some part is related to the groundwater contamination by not by the agricultural activity, but also about the human activity in urban area. Today's talk. So this is the result reported in 2012 in Nature Geosciences. And this is a groundwater depletion, special distribution of groundwater depletion by overpumping of groundwater. So you can see this most remarkable area is Asia, and here is India. And also this graph shows a very clear relationship between groundwater extraction from the aquifer and the groundwater depletion. It's very related. So you know from this result, so the groundwater pumping has a very huge impact on the groundwater environment, especially for coastal region. This is the case of Osaka. So in this graph, sorry that it's a little complicated and included Japanese, but so you can see this bar graph shows the groundwater pumping rate from the aquifer of Osaka. So you can see the significant pumping rate was observed in 1960s. From 1955 to 1965, this overpumping has occurred in Osaka region. And another information, this blue line shows the groundwater level change. So it is very, it responded to how much groundwater pumping out from the aquifer. So the groundwater level has decreasing, but recently it has recovered. And this brown line shows accumulated subsidence, land subsidence in Osaka area. So this was a very severe problem in Osaka. But recently it is almost stopped land subsidence. So the most severe period is from this period around 1960s in Osaka. And as I mentioned already, recently the groundwater has been recovered by the regulation of the pumping rate in Osaka region. The similar result was observed also in Tokyo, in the other big city in Japan. Yes, so from here, so I want to show some our observation result in Osaka area, and we have done some field campaign in Osaka area. About 2008 is almost whole part of the Osaka aquifer area, and in 2009, so we did some extensive, intensive observation at the near the. It is a major river inflowing Osaka Bay. This is the Yodo River. And another one, so which Shin-ichi mentioned, is the Yamato River. This is flowing here. Yes. And so today I'd like to show you the result mainly about the here in 2009. The groundwater was collected from surface shallow to the around 6 meters deep to the aquifer. And this is the cross section of the geological situation in this cross section. And in this figure, the blue layer shows from surface to about 20 meters deep from the surface. This is alluvial layer. And the second layer, this colored red, is from the 20 meter, more deeper than 20 meters. This fluvial layer. So this is the major aquifer in Osaka region. Yes, and this was observed the groundwater hydraulic potential distribution in this area. So in the horizontal axis, 0 means a coastline, and the right side means landwater. And you can see the hydraulic potential was lower in this middle layer, around 30 meters deep, than the surface and the more deeper layer. So it's like a circle of the lower potential. So based on this result, we can suggest the groundwater flow situation in this cross section. So, of course, some groundwater can flow from the inland to ocean, like this line. But in this section, this region, because the lower potential located here, so some seawater intrusion can be introduced to the aquifer like this. And also the surface, the shallow groundwater can intrude to the deeper aquifer. So the two type of flow can be assumed from this result. But that naturally the groundwater should discharge to the sea, from the land to the sea. But in here, so it is very there because the potential was still very low around here. So that means that still the past impact is remain. The huge overpumping impact was still remain in this region. And also, we tried to estimate the groundwater recharge age, the groundwater age using the flow column. So it can be applied for relatively new groundwater. So this is the same cross section of the potential figure. So you can see, you can simply remember that. So the potential was lower in this text. But so you can see the groundwater age is a little older in this layer, but almost similar between the surface shallower groundwater and deeper groundwater. But usually the shallower groundwater should be younger than the deeper groundwater. But so here the result is different. So that means as I already suggested by the potential figure, so the shallower, the younger groundwater might intrude to the deeper aquifer. So that this groundwater flow cause the age mixing of the different age of groundwater, and show this such of the profile. Yes, so the actual result shows groundwater age of shallower groundwater actually has a similar age with deeper groundwater. Yes, this homogeneous trend suggests surface water intrusion to river aquifer. Okay, so the next I will show you about some chemical property in groundwater. In this cross-section, a dash cross-section, firstly I show some chloride and phosphorus concentration in groundwater. So you can see it's the center, mid layer, around 30 meter deep, is highest chloride concentration and also highest phosphorus concentration. That means, because the potential was lowest in this layer. So the base of this chemical property, the highest concentration of both chloride and phosphorus were observed in the lower hydraulic potential groundwater around 40 meter deep. This shows the seawater intrusion to the aquifer occurs, and also because phosphorus can be higher concentration as a dissolved phosphorus in the more redox situation. So that means this layer should be the more redox situation due to the groundwater flow situation. Okay, so from here, so I want to move to the talk about the sewage impact. Okay, so as you know, the water pollution problem in megacities is very serious problem. Yes, but in case of Osaka, the construction of sewage system is now recently nearly 100% was maintained in the Osaka city. So this was most is maintained around 1980s. So improvement this caused significant improvement of water quality, especially for surface water quality. This is the Japanese, but you can see many lines. This is all the network of the sewage in the Osaka region. And this is total nitrogen concentration in Yamato River, so which Shin-ichi showed today, the major river inflowing to the Osaka Bay. So the concentration has decreasing. This river was one of the worst river in Japan in the past in the water quality, but now recently it has been improved due to the sewage construction, sewage network. Sorry, this is also the Japanese picture, but so the sewage sewage system has two different systems. So one is a combined sewage system. So that is the sewage line and also the rainfall precipitation line is combined. This is the old type of sewage. So, but this is the Osaka case because Osaka is a already developed city. So probably more than 70 or 80% of the sewage system is combined system. But in the newer, I see the newly developed city is now the separated system. So the sewage and the precipitation line has separated. So the potential new problems posed by the sewage is increase in sewage derived nutrient load. This is like a point discharge. The sewage effluent after treated sewage discharged to the surface water, the river and coastal area. And also, some part might influence on groundwater to the coastal area. Firstly, I want to show some of the effect of the degradation of sewage line because Osaka is an early developed city, so the sewage system is already old. So that has problem. So it can cause interaction between sewage and groundwater. And finally, I want to show this sewage impact on the coastal area. Yeah, also the rainwater inflow to the sewage line, and especially during the rainfall. After the rainfall, the sewage sometimes overflow, so overspec of the treatment. So the untreated sewage can discharge directly to the coastal area. This is another problem. Yes, and sometimes if the volume of the inflow on the sewage line increase, so it can flush the contaminants accumulated inside the sewage line. Yes. So this is a land use map in Osaka area, 1960s and 2000. So this period shows the Shin-ichi today mentioned already, and the urbanization stage is the first period. So still not so urbanized before urbanization. And so you can see, most clear thing is the residential area is changed drastically between this 40 years. So now much more urbanized in the city center and the surrounding area. And so based on the information, so we estimated how much nitrogen is loaded to the Osaka area. This is finally the loading to the underground. But you can see this is a first period, so before the significant urbanization. You can see the more the deeper color shows higher nitrogen loading. But after urbanization, the nitrogen loading has decreased. So can you imagine? Actually, we are based on our estimation. So 1960s is about the nitrogen loading is 50 ton per square kilometer per year. However, it has decreasing in 2000 less than 10 ton. So that is because the improvement of the sewage treatment systems in this area. So the sewage system contribute to reduce the nitrogen loading to the environment. Yes. And this is so we also estimated the different source of nitrogen in Osaka region, but most important and remarkable result is sewage. So because in 2000, so most of the nearly 100% area is covered by sewage system. So the nitrogen loading by the human sewage has decreased. So that's why nitrogen load has reduced remarkably, and total nitrogen load has decreased due to the sewage treatment systems. Yes. So I want to move back to the groundwater chemistry in this area. So I show the ammonium nitrogen and nitrate nitrogen concentration in the central section. So as you can see, the ammonium concentration highest in this the middle, around 40 meters deep layer. So which is characterized by higher salinity and higher phosphorus. But the nitrate nitrogen is a little different. So it is more higher in the surface, near the surface depths. So that means the shallower groundwater, less than 10 meters deep, is influenced by the infiltration of sewage. So that's why the higher nitrate concentration was observed in the shallower layer. However, in the deeper area, more than 20 meters, it's a more redox situation. So, of course, seawater intrusion occurs. And so that's why the denitrification might be occurred in layer and ammonium dissolution, because ammonium is also stable in the more redox situation. So that's why we observe the higher ammonium concentration in this way. This is finally I summarized all chemical species in this plot. So from surface to about 20 meters deep is alluvial layer, and we could confirm a little higher nitrate concentration. This should be caused by the infiltration of sewage into groundwater. However, in deeper area, deeper than 20, is fluvial layer is the peak in the chloride and phosphorus and ammonium also observed because it is more redox situation and seawater intrusion. And we also tried to apply the sulfate concentration and sulfate stable isotope ratio to detect some origin of sulfate in groundwater. So this left one shows the relationship between chloride and sulfur concentration. And the red line shows seawater mixing, seawater and rainwater mixing line. So if the plot is on this line, the sulfate concentration is influenced by the mixing of seawater. But if the sulfate concentration is higher than this line, so some artificial loading is suggested. And if the sulfate is lower than this line, so sulfate reduction is suggested. And this right figure shows the sulfate concentration and sulfate stable isotope ratio. I close up this area. Yes, so based on the sulfate stable isotope ratio, so we can know some different origin of sulfate. For example, in around 20 fermion is by seawater origin, but nearly the 10 fermion is by sewage. And if this ratio is very high, this suggests sulfate reduction process occurred. So these results looks like good support our former chemistry result. Yes, so now I'm talking about the interaction between sewage and groundwater. So this is the groundwater research, the special distribution map by SWOT model introduced by the Shin-ichi. The SWOT is a very good tool to estimate, especially the groundwater research. So it is possible to also combine with something like groundwater flow model, like water flow. It is very good to evaluate the from the research to discharge using this different type of model. And this is a hydraulic potential map. Based on these results, so we mapped the area, and its green color shows a little bit upland area is a sewage leakage to groundwater. This potentially occurred area. And this more coastal area, colored blue, this area is potential groundwater inflow to sewage line. But this groundwater is a little salinized, high salinity. So this is a schematic diagram, the cross section of the coastal area. So in a little inland region is ground surface is here, that the groundwater level is located lower than the sewage line. So that causes sewage intrusion to groundwater in the little inland upland area. However, in the coastal area, groundwater level is higher than the sewage pipe. That causes groundwater inflow to the sewage line. But that means saline groundwater inflow to sewage line. So probably that eventually increase the nutrient loading to the coastal area through the sewage. And also, finally, I want to show some results about the coastal area. Sorry, it is not groundwater. But how about the impact of the sewage to the coastal area? Eventually. So we did some campaign. So we did sampling of seawater sample. In this plot, this black symbol shows all sampling point of surface seawater. And you can see this green color shows sewage treatment plant. So we trace the nutrient concentration from the outflow of the sewage treatment plant onto the offshore, along with these three lines. Yes, so this is the result. So we observed three different lines from the sewage treatment plant to the offshore. So the horizontal scale in the zero means the sewage treatment plant. So as you can see, because this is a coastal area, so seawater, so the conductivity is lower, most lower in the inflowing point of the treated sewage, but it increases to the offshore. However, in nutrient, this is a dissolved inorganic nitrogen. It is highest in the inflowing point of the sewage effluent. Of course, this is a treated water, but it still has some nitrogen because the nitrogen needs more higher treatment technology. So it is difficult to remove all. So some nitrogen still remain and outflow to the coastal area directly. Yes, so you can see the higher nitrogen DRN concentration was observed from around 1 to 2 kilometers from the outflowing point, sewage effluent point. So this should be like an impact zone of treated sewage effluent. And the major nitrogen form is dissolved inorganic nitrogen. You can see, sorry, the scale is different. DON, this is organic nitrogen, and this is inorganic. Its main form is nitrate and ammonium. Yes, and we also try to monitor the rainfall, the impact. The before rainfall and after rainfall, we compare the result. After the rainfall, because discharge rate increase, so the more clear hard line was observed. So the surface layer is more fresh, but deeper layer is more silent situation. This is after the flood. So how it changed the impact zone in sewage effluent. This red line shows the base flow, the before the rainfall, and this blue line shows after the rainfall. So near the inflowing point, the base flow period is higher, but you can see the extent of the higher concentration increased after the rainfall event. In the base flow period, the concentration, this is ammonium, it decreased significantly very close from the shore, but after the flood, so higher concentration keep more offshore area. more than twice of the base flow. Yes, also we try to measure the nutrient profile in surface seawater and bottom seawater. This left one shows surface seawater data, and this is the bottom seawater data. The most big difference is ammonium concentration. You can see this surface layer is about 0.5 or 1 ppm in ammonium, but in this is near the bottom. Sometimes more than 50, 60, 70 milligram per liter ammonium was observed. So very high. So ammonium in bottom was tens of times of higher than that is surface. So it suggests that ammonium was supplied from the bottom sediment in this area. So this is a schematic diagram. So this is a sewage treatment plant. The sum of the nutrient has discharged from the plant directly. So this impact zone is around 1 to 2 kilometers toward offshore. But this nutrient is uptake by biology, for example, the phytoplankton. And phytoplankton finally sinking down and accumulated as sediment, and finally it decomposed. So it supply nutrient again. Yes. So based on this our results, so impact of the treated sewage effluent, so direct discharge, this reaches a few kilometers from the plant. However, the sewage effluent as well as coastal sediment, but this is derived from the sewage because of phytoplankton uptakes nitrogen nutrient by the sewage and accumulated the coastal region, and so this is indirect, not direct, but secondary source of nitrogen. So this is our result. So yes, so I want to conclude my talk. So nitrogen, the contamination in surface water has been improved by sewage treatment systems in Osaka. Yes, so but now Osaka is facing to some new problems for early developed the sewage system. So first one is sewage leakage to groundwater, and also as well as saline groundwater inflows to the sewage lines. For this, the line is already old. There are some cracks. And so sewage derived nitrogen load to coastal area, including the degeneration from the sediment. This is another problem. Yes. So thank you. Today's my talk is that's all. So we can...
Thank you, Mitsuyo. Well, nice presentation. I have some questions too, but please, if you want, you guys first. Do you have any comment? Questions? Okay, please.
Sorry, I forgot the number of the slide, but we showed here about the groundwater level trend, and it was decreasing in the first years, and suddenly from the point upward, the trend changed and it was increasing. I want to know about the strategy of that year. It was related to wastewater treatment and using this wastewater instead of the groundwater.
Oh.
It was in the first pages.
This page?
No.
No. You mean the some special distribution or long-term?
It was a figure with different here, and one of them that the red one. It was about groundwater level in different years. Yeah, and it was decreasing here, and from the point upward, the trend changed and it was increasing.
the geometric level after a specific period of time.
Yeah, I want to know about that year. I want to know it was the first of the wastewater treatment and using this wastewater instead of groundwater or something else.
I think that is.
It was in the first pages, maybe before 10.
Before 10.
It's not. It's not the five slides.
This looks the 5.
Yes, because it's depression and recovering of the water level.
It isn't. But it just show the long-term change in groundwater level. This blue line shows the groundwater level change.
The blue one is groundwater.
Groundwater
Yeah,
level.
I want to know about the year that the trend has changed and it was decreasing trend.
Yeah.
And
So this this decreasing.
And at the end, the trend change. I want to know about the strategy in that year.
Yes.
You started the wastewater treatment from that year and used that wastewater instead of groundwater or infiltrate it to groundwater or something else.
Sorry, so this figure doesn't related to the treatment, water treatment. So this is just the pumping, groundwater pump up date.
So you just increase the groundwater pumping. And what was the water that you used instead of this decrease in groundwater, the wastewater treatment?
Probably we changed to use more surface water than groundwater because groundwater level has decreased very significantly. Also, you can see the land subsiding was very serious. So they need to stop the situation. So they made some regulation of groundwater pumping. So there are some region, for example, the big company, a big farm, they reduce pumping rate. So that's why the groundwater can recover after the reducing of pumping rate.
And now, how much percentage of your use of from groundwater and how percentage of surface?
In Osaka.
So you mean what I use?
What I use?
Yeah.
I think less than 10% groundwater use.
From groundwater.
Yeah. Now much more using from surface water. Yeah, than groundwater.
Any other question or comment?
Just perhaps related to this slide, we have a couple of questions as well, but just on this slide, one thing that caught my attention is that you say that groundwater has been recovered by the regulation of the pumping rate.
Yeah.
So groundwater use, total cubic meters per day stayed the same. You just changed the way it was pumped. Or did you actually have additional groundwater sources coming to the sea?
So regulation means the regulation to reduce the groundwater usage. You use. So the people now more use the surface water.
Okay.
I have a question regarding the leakage from the sewage network. Because here in São Paulo, one of the main reasons for the shallow groundwater contamination is provoked by the leakage. São Paulo has a reasonable coverage of the sewage network. It's more than 85%. That is really nice. The problem here in São Paulo is the bad maintenance of this network. That also is a very old one. And normally the material that they construct this network was not so resistant to time. And it means that the leakage is expected from the system. When we analyze new neighborhoods that use the plastic material for the tubes, normally we observe that the concentration is really lower than the others compared to the downtown city that is normally the older system. I saw that you have this leakage of the sewage one problem that we have here is to calculate how much is the leakage in terms of the total amount of nitrogen or total amount of the sewage, the volume of the sewage that is go to the soil and can reach the aquifer as a part of the recharge. This is one big question. Also, in our case of the Bauru project, this is very important to understand the water balance and also the balance of nutrients. In this case, in the Osaka, do you have any calculation for the how much, how many liters per linear sewage you expect or something like that?
Yeah, so today I just introduced about this special map of the potential leakage zone, but Onodera sensei tried the calculation. So today I wrote the value of the how much is the leakage and how much nitrogen is derived from leakage.
We use we just estimate the water using in the areas, coverage areas. And also we have a treatment value in the plant. So then we compare that values. So that leakage or the inflow to groundwater to the sewage. So we can separate that water budget using the just general water budget.
Yes, we do the same here in the city of Urânia. That is one small city in the interior of São Paulo. That was possible to control the total water distributed to the city, and also you have the micro measurements of it for each houses, and it means that you have a relatively good control of how much water the city uses, and probably check the people how much water sewage they are generating, and also you have that the station for treating the sewage and compare the values. Yes, something like that. But you don't have any better system to get more precise numbers for this. But one interesting thing that I don't know in your case in Osaka, but in our case, this leakage is enough to keep an important plume below the city. Even in areas that you have good coverage of the sewage network.
I have a question. In your presentation, you said that in the deep portions of the aquifer, you identified the denitrification process. And I was thinking about the Bauru city, for example. I'd like to know which kind of tools you use in your project to identify that there is redox conditions, because one of the questions that we try to solve is if there is denitrification process in the Bauru system. So in your case, besides the chemical analysis, did you use other tracers to identify the nitrification and denitrification process in the aquifer?
Yeah, thank you for your question. So yeah, of course we firstly we analyze the chemical, very basic, the water chemistry and some parameter, redox, oxidation redox potential and dissolved oxygen, and also the concentration of nitrate, ammonium, and nitrite. And also we usually apply the nitrogen stable isotope ratio to nitrogen 15 of nitrate. Yes, this is a very good indicator to detect the denitrification signal.
Okay.
Yes.
Yes, because you have, according to the slide, you have higher concentration of chloride ammonium, and there is a
Yeah.
unified redox.
Yeah, phosphorus, yes. Based on this chemistry, so that this layer should be more redox. Now, of course, based on the DO and the ORP. But today, sorry, I didn't show the nitrogen, delta nitrogen 15.
Yeah.
Because so if the concentration is too low, we cannot detect, we cannot measure the isotope pressure. This is a problem. So
But you mentioned about the sulfate.
sulfate, yeah. Sulfate
Yeah,
is
the
also
sulfate,
another
Yeah.
possible
Right.
tracer, and maybe the ammonium, nitrogen, the nitrogen 15 of ammonium is also possible, but a little complicated for the pretreatment.
Okay.
But I think it will be possible.
Thank you.
Thank you.
Any other question? Another one? Yes, please. Go ahead.
You showed a map. It was the I think the result of the SWOT model, and it was about the groundwater research. It was a distributed map, and you told in another slide that in flood event, the interaction between surface water and groundwater can be effective, And I want to know how you calculate the map. Did you separate the dry season with humid season to consider this flood event, or no, just a normal situation?
This one?
Yeah.
Yeah. So in my talk, the SWOT model, we can, firstly, we can define hydrological response unit. So using the coverage, the topography, soil map, land use. So then that unit is basic, the calculation unit. So then that part, so we can basically calculate water budget. So then we can estimate each HRU, the groundwater recharge. So then basically monthly, also the daily, so that based on the time resolutions.
According to the average peak of the
Yes.
of the river.
Yes.
So most of the dry seasons and humid seasons
So-
are considered in this map.
Yes, so that if we can get the good data of the river discharge, so we can also estimate the daily or monthly discharge also.
So sorry, I ask again just to be sure that I understood correctly. So you use the average daily peak, and then again the average of during all of the days of the year, or in longer period, for example, several years.
Yes, that meaning that we can estimate the variation, daily variation and the monthly variation based on the time series, the regulate and the resolutions. If we calculate monthly data, monthly river discharge data, so we can estimate monthly water budget. So that means monthly recharge we can calculate. But daily, if we use the daily discharge, then calculate per day, so that we can output daily discharge.
Thank you.
Okay. Nice discussion. Okay, I want to say thank you for your presentations, both Professor Shin-ichi Onodera and Professor Mitsuyo Saito. Thank you again for giving us this opportunity to understand or know a little bit about Japan. Nice country, not just touristic one, but also for the groundwater information. And I want to say that this meetings, that is meetings of waters, Encontro das Águas, is an initiative for us to discuss about water in general, water resource, and the policy associated to governance of water. It means that in the future, our idea is to continue to invite people or present new results for projects, but mainly associated with these two initiatives that we are receiving from FAPESP, and that one is the SACRI project. SACRI project is just what you mentioned. It's a very large project. I suppose it is one of the largest projects in groundwater that we have in the history of the state of São Paulo, related directly to the research. And that is a 6-year project. You are just in the first year. Now you have the team almost completed. We received a lot of PhD students and postdoc students and new researchers. And there's an initiative from this university together with the other universities in the state of São Paulo, including UNESCO, Unicamp, Federal University of São Paulo, and here in Brazil. But also we have a very nice and good friends working with us from the University of Waterloo in Canada and Hiroshima in Japan. They are represent the group of Japanese researchers. Okay, we are just starting, and it means that you have a lot of things to discover and things to collaborate to get more information. The SACRI project, in terms of geographically speaking, you are studying the city of Bauru. Bauru is in the interior of São Paulo. It's 400 kilometers from the capital. It's a medium-sized city, but it's really important for the region. And Bauru is facing a lot of problem of water, not just during the droughts or the more dry years, but even in regular years, they have problems with water supply. The idea of the project is try to understand the situation, try to test new ideas or methodologies to improve the quantity of the water available for the system. Bauru has 3 different sources of water: surface water that supply 30% of the city, and 70% in terms of the public water supply. The Guarani aquifer supply another 70%. But it's also important to consider that the Bauru aquifer system, that is the large aquifer for us, the Cretaceous sandstone aquifer, that's unconfined in the majority of the area. In this aquifer, you have more 500 private wells that additionally supply another, in total, something like 20%. It means that the groundwater from the private wells is also important for the water security of the city. But the city suffered a lot of problem. The water service, the facility, the municipal facility, is trying to get more water from the very deep aquifer, that is Guarani, that has another problem, that is a fossil water. It means that it is a resource that has a deadline for the time. And they are losing 1 meter of the aquifer per year in the Piazonic level. They are losing. It means that it is one aquifer that has some, a time for finishing. If we not have any intervention for that. It means that it's a very interesting process that involves many people, and you have a lot of challenges to handle in this for this project. And also we have the group, but we will also invite people that want to know more about the project, or also to participate in the project. There are some possibilities, including some scholarships or some fellowships that can support new guys in the project. Okay, but that's thanks to FAPESP, because FAPESP is the main agency that supported this project and also the Spring project. Okay. Well, I say by that, perhaps in next time you can meet you again in this Encontro das Águas. That the idea is to have this event regularly, okay, here or in the other places, even in the interior of the São Paulo, Bauru, Unesp, or Unicamp, that's another partners, and or even in Diadema, that's the Federal University of São Paulo campus, Diadema. Okay. Thank you very much for the attention. Thank you again for your kind presentation, the opportunity to give us to understand a little bit about Japan. And yeah, thank you for everybody.